Hi everyone, this lesson is about periodic functions. In particular, we're going to be looking at transformations on a sine function. We can do virtually the same things with cosine. Tan is slightly different, but for sine and cosine, what I'm about to say applies to both. So the base function here is the function y equals the sine of x. And I'm sure you would remember that the sine function has a crest followed by a trough. This occurs between 0 and 2 pi on the x-axis, and on the y-axis we go from positive 1 at a maximum to, well, that 0 is a little bit in the way there, that was careless of me, to negative 1 on the y-axis. So that's our base function. Now these transformations have different effects. So the value of a, b, c and d will transform that base function. So a is the amplitude. Let's have a quick look at what amplitude does. So I have a GeoGebra worksheet here. Now I've got my base function drawn, 0 to 2 pi. I might stretch that out slightly so it's a little bit easier there. So I might stretch that one just a little bit too. Oh, I've lost the title. There we go. Now let's change the amplitude. I have a slider here to control the amplitude. If I make the amplitude 2, you can see that instead of the crest peaking at 1, the crest now peaks at positive 2. Instead of the trough at a minimum being -1, it's now at a minimum -2. I could send the amplitude all the way up to 5, so the difference between the x-axis, which is the equilibrium point, is positive 5 up or negative 5 down. We don't talk about amplitudes being negative. It's literally the height of the crest and the depth of the trough. So amplitude, of course, could be less than 1. I could have an amplitude there 0.4. So it's a very small crest and a very shallow trough. My amplitude could be 0, which is basically a perfectly flat straight line. If these were ocean waves, that would be a perfectly calm day with no ripples on the water. If I have negative amplitude, it simply turns the graph upside down. So instead of being, so let's have an amplitude of negative 2. So I take the value of the base function here, which is 1, multiply by the number negative 2, because a is a multiplying factor, multiplying by negative 2 times 1 gives me negative 2 at that point for the value of the transformed function. Over here, where the original function was value -1, -1 times -2 gives positive 2. So a negative amplitude reflects the graph. And that's interesting. And that's hopefully pretty easy to follow. The value of d here is a vertical shift. Let's go and see that. So I'll put my amplitude back to 1 so it doesn't distract us. Now let's try d. Here we go. If d equals 5, the entire graph has just slid vertically upwards by 5. Notice that my equilibrium position used to be here on the x-axis. My equilibrium position would now be running along here at the value y equals 5. Of course, sorry, I just grabbed the wrong one. I could also, of course, have a negative value for d. The vertical shift could be negative 5. So I've just slid the graph downwards there. I think d is the easiest of these to understand. And when I solve problems, d is usually where I start. Because if I can draw in an equilibrium line, it's kind of like the x-axis to anchor my diagram. The value of b here is related to the period of the wave. Now it turns out, working in radian measure, b equals 2 pi over t. T is the period of the wave. And on a diagram, I suppose I could mark in the amplitude here as being, there's the amplitude. If I had to mark the period on the diagram, the period of the wave, I use t for period. Sometimes the period is measured in time. And that would be the horizontal distance, if you like, for an entire crest and an entire trough. So b equals 2 pi over t. Let's go and take a look at what that does to the graph. So I'll just put that back up to where it was, and I'll change b from 1 to 2. Notice that where I used to have a single cycle, the green one is the base graph, I now have, there's a crest and a trough, and there's a second crest and a second trough. I have 2 cycles, 2 complete cycles, in the space where I used to have 1. So if you like, b is the number of cycles that occurs between 0 and 2 pi. If I bump that up to 5, there's the first, there's the second, there's the third, the fourth, and finally the 5th cycle. It doesn't have to be a whole number. I could have 2.5 if I can stop on 2.5. So there's a crest and a trough is 1 cycle, a second crest and a second trough is 2 cycles, and a crest is a half of the next cycle. There are 2.5 cycles here in the space between 0 and 2 pi. The value of b, in some respect, represents the number of cycles that will fit between 0 and 2 pi. Let me go and put b equal to, negatives are strange, we don't usually put negatives for b. Let me go and put b equal to 0.5. So I have a half of a cycle there. A single crest is a half of a cycle. Now going back for a moment to my notes, if I had that b equals 0.5, let's just change that to 0.5, then I could calculate by transposing here 2 pi over 0.5, that divided by that is going to be 4 pi. The period, and the period is how long it takes for a whole crest and a whole trough, looks to be 4 pi. Let's go back to my diagram and I'll scrunch the diagram in a bit to see where the end of that cycle was. This red one here, now a full cycle occurs after an elapsed time of 4 pi. So that's how that all works together. The final one that we want to talk about is the phase shift, which is C. Let me just tidy this up a little bit here. Yeah, messed that up a bit, didn't I? So that was B. Now this C is a bit of a strange one. It's called a phase shift. Now, if I go C divided by B, that more or less tells me the horizontal shift for the graph. Let me give you an example. So I'll put B equal to 1. Now let's move C equal to, I'll try to stop, well, 1.57 is half of a pi. So 1.5 is close to pi over 2. It seems like I have shifted my graph back on the scale by half pi. Did you see how the red graph slid to the left? And it's how far has it gone? Well, the crest used to be there, and now the crest is there at 0. So it's shifted by about pi over 2. If I send that all the way up to, actually I wonder if I can do something clever. It's never a good idea to try and be clever when you're in the middle of recording things, but let's just try. I'm going to write 6.28, which is, should have made that negative, 6.28, negative 2 pi, and I'll write 6.28 here. And for the increment, let's go 0.314, which is 0.1 of pi. So let's see whether or not my slider now will behave a bit more nicely for me. So there we go, 0.1, 0.2, 0.3, 0.4, 0.5, 1.57, or half of a pi. So it's moved nicely back by half a pi. If I go a bit more until I get, there it is, it's moved back by pi. So the The crest is now there. The crest used to be there. The crest is now back over there. It's moved back by a full amount of pi. If I go 2 pi, it coincides again because 2 pi is a whole cycle. If I have negative values, then it goes that way. Now remember, that was all when b equaled 1, and I said that the phase shift or the horizontal shift was c divided by b. Well, remember, if b scrunches things up a bit, then the value of c, it's going to have to change correspondingly with b. This is why phase shift is a little bit more tricky. It's c divided by b, and so it depends on how long the waves are too. Most of the time we don't get too bent out of shape over the phase shift. Now, here's one, and of course it's got a phase shift, doesn't it? Let's identify what we're doing here. This would have an amplitude A equal to 3. It would have B equal to 1, C equals pi over 4, D equals 2. Now we have to try and sketch this thing, and I note that the base function is a cosine function. So let's see how I would go about sketching this. And my diagram is going to be a little bit rough to begin with, I think, but that's okay. So I'll start with a cosine function. Now I know that cosine ranges from +1 to -1, and it ranges to 2 pi. So I'll mark in pi, and I'll split each of those in half as well. The cosine function begins at +1, drops down to 0, down to -1, back to 0, and back up to there. And this is my base function. That's a bit rough, but it's close enough. Now the first thing I'm going to do is my vertical shift. My vertical shift, I haven't left myself enough room to do a vertical shift. Let's see if I can lasso this picture and move it down a bit. Ah, wonderful. I'll give myself a bit more room here. So that would be 2, that would be 3. I may even need more room. I'll rub some of these out to give myself some working space. With a vertical shift of 2, my equilibrium is going to shift upwards by 2. This is where the equilibrium would be. That's where it would be now. The next thing I'm going to think about is my amplitude is 3. So instead of going up and down by 1, I need to go up and down by 3. I really didn't give myself enough room here, did I? Compared to the starting point, a cosine graph is up by 1. So compared to that starting point, I need to go up by 3 times that. I need to go up to here. So my graph will actually be, that's the amplitude. Haven't done the phase shift yet, I'll do that last. Compared to here, that's on the equilibrium. So 3 times 0, 0 difference from the equilibrium is there. Then at this point, I have an amplitude of -1. Well, from here, that's 3 steps down. 1, 2, happens to coincide. This one's back to equilibrium, and this one's back to +3. That's almost my graph, but I haven't accounted for the phase shift of pi over 4. A pi over 4 phase shift, now fortunately b equaled 1, so if b equals 1 I'll have the same period, 2 pi, and a phase shift of -pi/4 is going to shift the graph by this much. That's pi/4. So that point is actually going to be shifted sideways. That one's going to be shifted sideways, that one's going to be shifted sideways, that one's going to be sideways, and that one's going to be sideways. That's where my actual graph is going to be. And that's what I'm going to try and sketch. Wish me luck. and we would be minimum there, and we would be back up to there, and we would be back up to there. Now, of course, that's a very rough diagram. The best way to do this, as long as it's tech active, is to use your graphing calculator. So here I go, 3 multiplied by the cosine of x minus pi on 4 plus 2. I will limit the domain, so put the comma, then square brackets, the domain is from 2 to 2 pi, and then close the square brackets. That limits the domain. Just be careful your calculator is on radians, so I'll hit enter, and I'll draw that. Now my view window's a bit off. Let me check the view window. I've gone from 0 to 2 pi, so to about 6.5. 2 pi is 6.28. I think I'm going to need to go as far as low down as -1 and as high as 4. So let's drop to -1 and 4, and I've got 0.5 as the increment. What did I mess up? I didn't get high enough. Oh, because that's up to 5. Try that again. Maximum value of 5. There's my graph. Isn't that delightful? Now, I could, of course, use this graph with GSolve to calculate various other answers. For instance, let's say I wanted to know the x value where the y value equaled 3. So I'd go GSolve, move to the right. I'm going to give you a y value and I want you to calculate the x. So give me the y value of 3. And when y equals 3, x is 2.016. Now it would occur again over here. I can press the right arrow and it jumps across and says y is still 3, x is now 5.838. So that's how we can use our calculator to do these things accurately, but it is important that you have an understanding of each of these values A, B, C and D and the effects that they have. Okay, this has been a pretty long one, so thanks for watching and see you next time.